Okay, symplectic form. Well, let's introduce some other notation, phi. And that's a linear transformation, or bilinear mapping of V cross V to a set of all real numbers. Well, if this is symplectic, the first property that must be satisfied is, of course, that phi is bilinear. And of course, that phi is skew symmetric. Well, for a skew symmetric linear transformation, that is denoted, for example, if phi of vectors u, we had a transformation here, vectors u and v, the skew symmetry will of course demonstrate itself for this, in which we would switch the order in which we transform the vectors. And the third property that a symplectic form must satisfy is that it's non-degenerate. And of course, for it being non-degenerate, if we use the same example, phi of transformation phi vectors u and v equals 0, then either vector u or vector v must equal 0 for the non-degeneracy. So, a particular example of a symplectic form is, let's just say, if we define this particular, if phi naught, the transformation from R2, or R2 cross R2, is set R, where this, of course, is given by two vectors u and v, where, of course, if vector u equals a1 and a2, and v equals v1 and v2, and we define, for this particular example, this is a symplectic form, or symplectic mapping, which should be a1 times b2, a2 minus b1, which of course, that is the determinant of the 2x2 matrix, where of course the columns of the matrix would be the entries of both vectors u and v. And this particular example can be generalized to, of course, any vector space that is even, of an even dimension. So, if, for instance, we had, I'll introduce some new notation. I'll just use epsilon, for instance. Say that epsilon is R2n cross R2n, to, of course, transformation to the set of all real numbers, where, of course, epsilon is two vectors. We can use, of course, u and v. Well, for this abstraction, if, of course, we rewrite this vector u, A1, represented as a column, to, of course, big N, vector V, B1, B, well, in fact, it should be 2n, corresponding to the dimension of the vector space. Well, what we would get, of course, by generalizing this symplectic form, of course, A1 times B1, A2 times, or minus A2 times B1, and plus, so on and so forth, to we would have, of course, A2n, actually, 2n actually should represent times the vector. Well, the reason why it should be 2n minus 1 is for such, and we'll write that out here in a minute to demonstrate. Minus A2n times B2n minus 1 for, of course, this generalization. And this is, of course, the determinant for any matrix in which, of course, that is of dimension 2n by 2n. And hence, this, of course, implies something, of course, that the dimension of any two vector spaces must be even in order to define a symplectic form. We can't, if it's not even, then of course skew symmetry not apply. That's, of course, distinguishes the difference between a symmetric or skew symmetric form of a mapping. So, moving on to this particular example, and for the symplectic mapping, if I constructed a picture, if I use these two vectors, u and v, and let's just say u, vector u is here, vector v is here, well, of course the determinant gives us, tells us how, of course, the area of how some oriented area changes, of course, by the use of a matrix. Oriented area of two vectors, and of course this determinant would give us, or the absolute value of this determinant would give us the oriented area of the vector, oriented area between the vectors u and v. So, that representation of the symplectic mapping, of course, corresponds to this. For this particular example, of course, this goes on to higher dimensions, but I don't think I can construct a graph for 2n by 2, a dimension of 2n. So, moving on to here, on down through a line, you can also use pair, such as an inner product space, for here, defined by, of course, these particular properties. We can use, we can say that Rn, comma phi, well, I'll use some different notation. I'll use phi, I'll use epsilon for this generalization. This, of course, is a vector space. And of course this can be verified, again, by showing that the standard operations are true for this vector space. And this corresponds to, of course, what this vector space actually is. And if we had, of course, by using phi naught, phi of v cross v is the transformation of. If we use that notation, we're going to look at Cartesian product of v cross v, where this, of course, would be given by phi of two vectors. We can call them, of course, or one particular vector. And we can, of course, make sure that we know that we're working with the vector space, the symplectic vector space, big phi, or of course, this is a finite dimensional symplectic vector space if it is a linear isomorphism. And we enacted this transformation, and the way that that is true is if we enacted this transformation on a particular vector, v, we went on to, and this corresponded to some element, b, with respect to that vector, where, of course, this element b with respect to b is an element, of course, of this transformation, which, in fact, that is in fact implicit. But for this particular case, this is a linear isomorphism, of course, for all vectors which are an element of the vector space V. And, of course, with it being a linear isomorphism, as if we enacted, of course, this component acting as a transformation. It would be a linear isomorphism if the following here would be true. That this is in fact just phi of the vectors v and u. Of course, this can be proven, of course, by showing the generalization, of course, the transformation and such for this particular element, which, of course, it acts as a transformation, or is a transformation. And that's just one. That is just, of course, the description of the condition that must be satisfied in order for, of course, a symplectic vector space to be a linear isomorphism. So, another interesting thing is, of course, going back to, of course, linear transformations and other general concepts of vector spaces. We had, of course, sets of vectors that were orthogonal to another set of vectors, of course, that corresponded to that set of vectors. Well, if we had a set of vectors, let's just say if where, of course, B was a subspace of this vector space, well, for this particular vector space, it's not just called, we can not only just define an orthogonal vector space as it's skewed orthogonal. Of course, and that goes back to, of course, the property of skew symmetry. And the skew orthogonal subspace for its corresponding vector space B, of course, would be denoted by B phi. Standard way of writing the notation. And of course, this would be the set for all vectors, of course, that are an element of the space B for all vectors, of course, U that are an element of B, such that for all the vectors that are an element, of course, of subspace B, well, by using this bilinear mapping, this function, of course, equals 0. And then, of course, there are a series of course, different properties that, of course, correspond to a subspace of the symplectic vector space, such as, of course, there are things to be proven, and this is, of course, can be proven by, of course, choosing any arbitrary or ith vector of each particular set and showing that this is true, as long as, of course, it corresponds to the condition of the symplectic vector space. Now, and of course, other things, of course, a skew orthogonal set corresponding, of course, to another subspace of the symplectic vector space would be, of course, if we had a basis for a symplectic vector space, and of course we had a subspace that was, of course, an element of the vector space for the symplectic vector space, in particular this vector space, then a proposition or theorem, of course, that can be easily proven would be that the skew orthogonal set that is, of course, this skew orthogonal subspace of that basis is also equal to the skew orthogonal subspace to a certain subspace out in that vector space. Not entirely coherent, but it's okay. Let's just say if S was a basis, and of course we used, of course, a notation. If we had a subspace, which is a B, which is a subspace of V, then this skew orthogonal complement of this basis is also equal to the skew orthogonal complement of that particular subspace, of course, corresponding to the elements and the symplectic form of this vector space. And that, of course, could be proven, of course, again, similar to, of course, this proof, of course, has a bit more outreach, of course, with showing the generalization of each particular vector in this set. But moving on to another particular thing is, of course, the symplectic vector space, or can also have matrix representations, or, of course, the bilinear mapping of the symplectic vector space. And if we have some room back here, and we do.
Okay, start over.